Hello friends, welcome to the today's lecture. Here if you recall, we have discussed in last class the concept of functional, and we have seen that in calculus of functional, the branch calculus of variation discuss the methods which discuss the maxima and minima of a given functional, and we have seen that the methods of finding the maxima minima of functionals is closely related to the concept of finding maximum minima of functions. So in last class we have discussed say relation between function and functional, and also we have seen the definition of increment in terms of function. So it means that delta x, and the corresponding analog version in terms of functional, that is delta y, where y is the argument of a given functional. So here we continue that lecture into today's lecture. So today's next thing we want to discuss is the continuity of a function. In previous class we have just given the just a idea of what is continuity. So if you look at the continuity of a function, then we can say that a function f(x) is called a continuous function if for a small change in x they correspond a small change in the function f(x). So that is the definition of continuity of a function. In then we want to look at the analogous version of the continuity of a functional. So we can define the continuity of a functional in a similar manner and say that a functional z(y(x) is called a continuous functional if for a small change in y of x they correspond a small change in the functional z(y(x). Now in terms of function, it is quite obvious that if there is a change in x, say x to x plus h, then what is the change in function? So f of x plus h and f of x. Now here we want to see that what small change in y of x we are referring. So here we may ask this question, that what changes of the function y of x, which is the argument of the function, are called small, or what curves y and y1 are considered close or only slightly different. So it means that if you talk about function, then in function x, a small change is x plus h, but in terms of functional, your argument is y of x. So what is the small change in y of x? So it means y of x and the small difference in y of x, that is say y1x. So how in what way we can say that y and y1 are small enough? Here regarding the closeness, we may consider the function yx and y1x are close if the absolute value of their difference is small. So it means that the modulus value of yx minus y1x is small for all values of x, then we can say that okay, these two functions are close enough. Now but if we take this definition as closeness, then look at this functional. So zyx is equal to x1 to x2 f of x y dash dx. Now it may happen that the function like this, which are small, which are close enough in this sense, may have possibility that their derivatives are quite far, or we can say that if you look at this particular graph here, that here you just write down this thing, and here we can define, this is your, suppose this is y of x, and then we can define your another y1x like this. So here we can say that let us say that this is your okay. So here this yx is this graph y of x, and y1 is this spiral one, so it is y1x. Now I can say that if this is say distance is like 2 epsilon, so we can say that all the time y of x minus y1x, if I look at their derivative, their difference is less than say epsilon. But if I look at the any point, say let us say this particular point, then though their functional value is quite say same, quite close to each other, but if I look at the value of their derivative. So it means that at this particular point your let us say call this point as say x1. So at this particular point this is your y dash x1 and this is the value of y1 dash x1. So here the slope of curve y1 and the slope of curve y is quite far to each other. So in this sense we can say that this functional in this sense we can say that your y and y1 are not close enough in the sense of first order derivative, and it may happen that if we consider a functional which involves in terms of say y dash, so let us, if we consider z y of x like this equal to say a to b, you take simple y dash x d of x, you can take any function alpha x y dash. So in this sense if we take closeness only in this sense, then this functional may not be continuous at all. So this compel us to define our definition of closeness in a more suitable manner. So we can say that therefore it is required that for closed curve not only the absolute value of the difference should be small, but the absolute value of the difference should also be small. So it means that not only the y their functional value is same, but their tangent is also close enough to each other, and in it may happen in some kind of functional which may involve say mth order derivative of argument y. We may define the definition of closeness as the as follows, that the difference, the absolute values of the differences yx minus y1x, y dash x minus y1 dash x till ymx minus y1 mx are small. So based on these definition we can define define the definition of closeness in the as follows: the curve y equal to yx and y equal to y1x are close in the sense of zero order proximity if the absolute value of the difference yx minus y1x is small. Similarly we can define the first order proximity, that the curve y equal to yx and y equal to y1x are close in the sense of first order proximity if the absolute value of the difference yx minus y1x and derivative, that is y dash x minus y1 dash x, are small. So in keeping this track we can say that the curve y equal to yx and y equal to y1x are close in the sense of mth order proximity if the absolute value of the differences, this is the zeroth order derivative, so yx minus y1x is small, y dash x minus y1 dash x is small, till the mth order ymx minus y1 mx are small. So we may define our closeness in the sense of zero order proximity, first order proximity, or up to mth order proximity depending on the definition of the functional. And we may observe here that if we may observe from these definition that closeness of two curves in the sense of mth order proximity implies the closeness in any lesser order of proximity. It means that if we consider that two functions say yx and y1x are close in the first order proximity, then it will be close in the zero order proximity. Similarly if y and y1 are close in the sense of mth order proximity, then they will be close in the m minus 1th order proximity and any order which is less than m. So now with the help of the closeness in the sense of mth order proximity, we may define our continuity of functional as follows. So first we define what is continuity of a function. So a function fx is called continuous at x equal to x naught if for any epsilon greater than 0 there exists a delta greater than 0 such that modulus of f of x minus f of x naught is less than epsilon whenever x minus x naught is less than delta, or I can say that the functional value differ by at max by epsilon whenever the argument is difference of the argument is less than delta. Similarly if we go to the definition of continuity of a functional, we can say that a functional zyx is called continuous at y equal to y naught in the sense of mth order proximity if for any epsilon greater than 0 there exists a delta greater than 0 such that the difference in functional value corresponding to y of x and y naught x is less than epsilon whenever modulus of y of x minus y naught x is less than delta, y dash x difference between y dash x minus y naught x is less than delta till absolute value of ymx minus y1mx is less than delta. So, that is the continuity of a function in the sense of mth order proximity, and we can here we have assumed that this y of x is taken from a class on which this functional is defined. So, that is the only condition on these y of x. So, here we are discussing an example of continuity. So, here the example which says that show that the functional j y x equal to 0 to 1 x cube square root of 1 plus y square x d of x defined on the set of function y of x equal to c01, and this c01 is the space of function which is continuous on closed interval 0 and 1, and we want to show that this functional j(y)x is continuous on function y naught x equal to x square in the sense of 0 order proximity. So, it means that let us take a arbitrary function y of x in the proximity of in the neighborhood of x square. So, let us define y x is equal to x square plus c u of x, where c is an arbitrary small parameter, and here ux is also a member of c01. It means that ux is also a continuous function defined on closed interval 0 to 1, and then we want to check the functional value on this y of x. So, j y of x, which is nothing but j of x square plus c u x, and by the definition of function you can write it 0 to 1 x cube 1 plus x square x plus this is x square plus c u x square under root of this thing d of x. So, here if you take the limit c tending to 0, in that case your y of x will tend to x square, right. So, let me write it here. We are looking at this functional j of y of x, that is 0 to 1, and here it is written as x square x cube under root of 1 plus y square d of x, and we want to check the continuity of this functional at for y naught at y naught x equal to x square. So, we want to check whether this functional is continuous at this or not. So, for this you take a arbitrary function, say y of x, which in the neighborhood of x square. So, let us say that it is simply y naught x plus say some c times some another function, say let us u of x, and here since y of x is also a member of c01, so here y of x is a member of c01. So, we can say that this u of x is also a member of c01, means ux is also a continuous function, and then we try to show that if c tending to 0, then this y of x is tending to y naught of x. So, it means that if I take this c is very small, then we can consider that y of x and y naught x are close enough in the sense of 0 order proximity. So, we can say that here the difference of is what, y of x minus y naught x, and that is nothing but c of u of x, this thing. So, if c is going to 0, then the difference is also tending to 0. So, we can say that here y of x is close to x square in the sense of 0 order proximity. Now, we want to check that the function is also continuous in the sense of 0 order proximity. So, for that you calculate the value of j of y of x. So, this is 0 to 1 x cube and under root now 1 plus, now y of x is given by this. So, it is x square plus c u of x whole square d of x. Now, we try to say that if this y is tending to y naught, then what is the functional value? It will change to it will go to the value of jy naught or not. So here we want to see the change, that limit c tending to 0. Now j of yx will be what? So here you can take the limit inside 0 to 1 x cube, and limit, if you take the limit inside, it is 1 plus, and this is x square, because limit, if you take inside the limit c tending to 0, then this part is simply gone and it is this. And if you look at by definition, it is nothing but j of x square. So you can say that functional is continuous at y naught of x equal to x square in the sense of 0 order proximity. Now if you look at this closeness in terms of mth order proximity, we can also define the distance between two functions, say y1 and y2. So let us say define distance between y1 and y2, and these y1 and y2 are function of some function space, let us call it S, which is defined on say a to b, and we can say that it is nothing but maximum of x between a to b, and here we are considering the difference between y1x minus y2x. So if we calculate this quantity, we can say that this is the distance between y1 and y2 in the sense of 0 order proximity. Similarly, we can define the distance in the sense of mth order proximity in a similar way. There we can consider this as summation, say p equal to 0 to say m, and here it is maximum of x less than or equal to a to b, and y1 x minus y2 x, and here we are considering up to say mth order derivative here. So if we calculate this value, then we can say that your y1 and y2 distance between y1 and y2 in the sense of mth order proximity. So this is in the sense of closeness defined in the mth order proximity, we can define distance between two function in the sense of 0 order proximity and hence mth order proximity. Now just moving on to the next concept, let us define what is linear functional. So please recall that a function is called linear if we have this property that y of alpha x plus beta z is equal to alpha y of x plus beta y of z, where x and z are the point in the domain of y, and alpha and beta are just arbitrary constant. So in a similar manner, we can define linear functional as that a functional z y x is called a linear functional if we take two functions y1x and y2x from the domain of z, and the value of z of alpha y1 plus beta y2 is equal to alpha times z of y1 plus beta times z of y2, and here alpha and beta are arbitrary constants. So if you look at these two definitions are almost similar. Now going on to example, the first example we can consider as the functional defined on f is the value of f given at a particular point x naught, where x naught is any point between this interval a b. Now this I can define in this manner. So here if you look at phi of f, it is defined of f of x naught. So here if I take say alpha f1 plus beta f2, then I can write this as alpha f1 plus beta f2 evaluated at x naught, and this can be written as alpha f1 x naught plus beta f2 of x naught, and this I can write as alpha phi of f1 plus beta phi of f2. So we can say that this functional phi of f is a linear functional. Okay. Now here we can also see that so far we have represented our function in terms of integrals. So here this also can be represented in terms of integral, and we can write this as f of x naught as a to b. Now here we can take the help of Dirac delta function, delta x minus x naught f of x d of x. So here this function can also be written as definite integral. The only thing is that here we are using the Dirac delta function. So this we can see that this is also a functional. Similarly, the integral phi of f, which is defined as a to b alpha x f of x dx, is also defined a linear functional. You can check in a same way, you just go and check the definition, okay. And similarly, this third example and fourth is also third, which is defined as j y x equal to a to b x cube 2x y x minus 3y dash dx in the space of C1AB. Here C1AB is the space of continuously differentiable function. It means that the all those functions whose first order derivative is also continuous. So in that sense, this functional is also a linear functional. But if you look at the last example, that is j y x equal to 0 to 1 x cube 1 plus y square x to power 1 by 2 dx, it is not a linear function, because if you replace this yx by say y1 plus y2, taking say alpha equal to beta equal to 1, then you can check that it is not equal to j of y1x plus j of y2. You can check easily, okay. So now let us recall what is the concept increment of function, and we can define with the help of this the increment in terms of function also, and that is known as variation. So increment of function is defined as the change in the functional value when there is a small change in the argument of the function. So here delta f is defined as f of x plus delta x minus f of x. So here your argument is changed by small difference, that is delta of x. This is the increment in terms of x, and if this increment is written as this a of x into delta of x plus bx delta x into delta x. Here ax and bx is defined as follows, that ax is independent of delta x and b is tending to 0 as delta x tending to 0. Then in this case we can say that this function f is called differentiable, and what is the differential of this, and we can say that the part of the increment which is linear with respect to delta of x, that is this part ax delta x, is called the differential of the function and denoted by d of f, and we can say that d of f is equal to f dash x delta x. So how we can look at here, let me write down this. So here your delta f is given by a delta x plus b x delta x delta of x. So what we try to do here, let us say divide by delta x here. So if you divide by delta of x here, so that will be simply this, and then you take limit delta x tending to 0, then this will this is denoted as d of f, and this is nothing but df by d of x, and it is a because this part is simply vanished to tend to 0 as limit delta x tending to 0. So we can say that this a is nothing but f dash x. So a is equal to f dash x, and we can say that this d of f is given by f dash x delta of x. So that is what how we define differential. So differential of the function which is denoted by d of f is given by f dash x delta of x. So that is how we define increment in terms of function. So in a similar way we can define increment of functional as follows. So here increment of functional is defined in a similar way, that argument is say incremented by say delta y. So and look at the functional difference between yx plus delta y and y of x, which is given as delta of z equal to z of y of x plus delta y minus z y of x, and if this increment is written like this, that is delta z equal to a yx comma delta y plus b yx comma delta y and maximum of modulus value of y delta y, and if we consider this function as linear with respect to delta y, and maximum of delta y denotes the maximum value of delta y, and this b is tending to 0 as maximum delta y tending to 0, then this part which is linear in terms of say delta y and it is the principal part of the increment, is called as variation or say increment of the functional z, and it is denoted by delta of z. So, we can define variation of functional is the principal part of the increment of the functional which is linear in delta y. So, we can say that this is the part, it is known as principal part of the increment delta z, and it is linear in terms of delta y. So, this a y x comma delta y is denoted as variation of the functional z. Now, we can also define our variation of a functional in other sense. So, for that we please recall that if we want to define, we have seen how to define the differential of function and differential in terms of functional. So, now we consider the alternative way to define increment in function and increment in functional. So, if you look at your d of f is defined as f dash x delta of x, and which is defined in the sense of this, that delta of f equal to a delta x plus b x delta x and delta x, where a is a linear with this independent of delta x and linear part, and b is tending to 0. So, here we have an alternative way to define this differential. For that we consider function evaluated at x plus c delta x. Here x is fixed, delta x is fixed, this parameter c is a varying parameter, and if you calculate the derivative of function f with respect to c at c equal to 0, then it is coming out to be the differential of the function f of x at the point of x. If you look at, just look at here, find diver by diver c of f x plus c delta x evaluated at c equal to 0, then we can differentiate this using the differentiation of composite function, and it is coming out to be f dash x plus c delta x evaluated at c equal to 0 into delta of x, and it is coming out to be that this quantity evaluated at c equal to 0 is nothing but f dash x, and we can write it f dash x delta x as d of f x. So, it means that we can also define differential in this in the sense of this quantity. Similarly, for a function of several variables, that is z equal to f of x1 to xn, we can also define a differential in a same way. For that you consider this function f of x1 plus c delta x1, x2 plus c delta x2, and so on. So, here delta x1, delta x2, delta xn are all fixed. Similarly, x1 to xn are all fixed. Only thing is that c is a parameter which is varying. So, if you find out say derivative of this with respect to c and take c equal to 0, whatever you will get, that is nothing but differential of this function f. So, in a same way we want to define the increment or variation in terms of functional. So, here if the functional has a variation in the sense of principal linear part of the increment, and then its increment will be given by delta of z equal to z y x plus c delta y minus z of y x. Now, here y x is fixed, delta y is fixed, only c is varying. So, by definition of increment, this can be written as a of y c delta y. Only thing is that here this increment is replaced by c delta y. So, in the definition also delta y is replaced by c delta y. So, you can say that it is a y c comma c delta y plus b y comma c delta y modulus of c maximum of modulus of delta y. And if you find out say derivative of this with respect to c, then it is what, limit delta c tending to 0 delta z by delta c, which is nothing but limit c tending to 0 delta z by c. So, delta z is already defined by this increment, and then you divide by c and take the limit c tending to 0. Then this can be written into two part, one part is corresponding to this linear part, another part is this. Now, here as limit c tending to 0, this b y c delta y is something which tend to 0 as C is tending to 0. C is tending to 0 means C delta y is tending to 0, and hence by definition your B is tending to 0. Whatever we are keeping here, that is a bounded function, that modulus of C upon C is bounded by 1, and maximum of delta y is also some fixed quantity, so it is also bounded. So as limit C tending to 0, by the definition of B it will tend to 0. So what is left here is a y delta y, because this A is linear with respect to second argument, so C will be taken out, and you can say that it is nothing but C times a y delta y divided by C. So C will cancel out and we have a y delta y, and it is nothing but variant or increment in the functional. So you can say that increment in your functional can be given by derivative of delta derivative of z with respect to C. So here we can say that if we summarize this, thus if there exists a variation in the sense of principal linear part of the increment of the functional, then there also exists a variation in the sense of the derivative with respect to the parameter for the initial value of the parameter, and both of these definitions are equivalent. So we can summarize and we can write that the differential of a function can be written as f dash x equal to limit C tending to 0 divided by dou C f of x plus C delta x, that is in the sense that is for function. So in a similar way we can define variation of function as this, that variation of functional z y x is given by derivative of z of y of x plus C delta y with respect to C at C tending to 0, or you can say limit C tending to 0 divided by dou C z of y x plus C delta y. So and with the help of increment of variation we can define a point which is maximum point or minimum point. So this portion this we will discuss. So in next class, so here we have a two definition of variation of a functional. This definition we find it useful because it is not all the time possible to represent your increment delta z as this particular form. So in some cases where your functional is quite complex, then this form is quite difficult to achieve. So there we find out the increment of functional using this later definition which we have just shown. Okay. So so we will use this as a definition of finding variation of functional. So in next class we will continue after this, and we define what is maximum and minimum value of a functional, and discuss the necessary condition of for maximizing the functional, that is Euler equation. So so here we today bind up our lecture and we will discuss the necessary condition in next class. So thank you for listening us, and thank you.